So we looked at a silly example of a hypothesis test in the last video. Now let's have a look at some real hypothesis tests. And the first one we will look at is called a one-sample t-test. Now, what do I mean by a real hypothesis test? This is a hypothesis test that follows certain assumptions and we can get our p-value exactly from online calculators. And a one-sample t-test goes like this. So we have some data and our null hypothesis is that our mean, population mean, mu, is equal to some specified number. Okay, mu star. Our alternative hypothesis, there are actually three possible alternative hypotheses, three opposites to this. So we can either have that the population mean is not equal to that specified number, or if we know something about our data, if we are asking a certain type of question, maybe we know that the population mean can only be less than that certain number, or we don't care if it's larger than that number, we only care if it's less than that number. So our alternative hypotheses could be that mu is less than that specified number, not equal to that specified number, or greater than that specified number. And this is not just a matter of semantics. This is something that actually affects how we interpret the results. So choosing which is your alternative hypothesis out of this is very important. It's so important, in fact, we have different names for them. So we say that if your alternative hypothesis is the not equal to option, that is a two-tailed test, and you'll see why in a bit. Otherwise, you're dealing with a one-tailed test. So knowing if you're doing a one-tailed or a two-tailed test will change how you interpret the results. Let's look at an example. So a factory producing factories claims they have a lifespan, so an average lifespan of 48 hours. There are reports that the batteries are actually dying quicker than this. So a government inspector is sent out to test the claim. She takes a sample of 18 batteries and records their lifespans in hours. So how long do they last for before they die? And she records the first one lasts 40 hours, the second one lasts 43, then 45, then 50, and so on. Now she wants to know from that sample, is the null hypothesis that the population average of all the batteries the factory producing, is that equal to 48 hours? Or is it, as the reports are saying, less than 48 hours? So she has some prior knowledge that the population mean might be less, and she's asking the question that is the population mean less, because as the government inspector, she doesn't care if the factory's producing better batteries, she just cares if they're lying and producing worse off batteries. So this is a one-tailed test. Let's say the inspector wants to be 95% confident in her findings. If she wants to be 95% confident in her findings, she chooses an alpha level of 0.05. So that's 1 minus 0.95, so the 5% that we care about. So our rejection region then, if we get a p-value which is within 5%, that's small enough for us to say the null hypothesis is probably wrong. So let's perform this test, and we're going to perform this test using an online calculator. So I just go to Google and I'm going to just type in a one-sample t-test calculator, and I'm going to click on one of them. I've been on this one before, so I'm going to use this one, but all of these should give the same answer. And it explains a bit about what's going on in the background. You don't need to know that, okay? You just need to know how to interpret the results. So take me to the calculator. So this one sample t-test calculator is asking, what is the population mean that I'm comparing to? And I'm going to type in there 48. What is my sample? So my sample here, I'm just going to paste that in, is the 18 observations that the government inspector took. It's then asking me a significance level and whether it's one-tailed or two-tailed. Now for online calculators, always click one-tailed, even if you're doing a two-tailed test, because these online calculators will skew your results. and the significance level is 0.05. Then we just click calculate, and that's done it for us, and this has given us a t-value of that. Don't worry about that, but the main thing is here, the p-value is 0.000802. So that's the important thing to take from this. Kind of ignore the rest. How do we interpret that? So based on that sample, we can calculate some sort of statistic. We call it a t-statistic. And we know that under the null hypothesis, it will follow this kind of curve. This is called a t-curve. And we're asking, is our p-value within that rejection region of 0.05? That was how confident we wanted to be. And our p-value, we got 0.0008. So we were in that rejection region. That means we had a t-statistic which was that unlikely under the null hypothesis. So the probability of observing what we observed, given that the null hypothesis was true, so this green curve, was equal to 0.0008. And that was less than our alpha value of 0.05. Therefore, that is, seeing what we observed is so unlikely that that green curve, our null hypothesis, is probably wrong. And we have enough evidence to reject this. And if we reject the null hypothesis, the only other alternative is the alternative hypothesis. So in this case, the government inspector can be 95% confident that this battery company is lying and their population mean is less than 48 hours. Let's do another example to really cement this in. So a maths teacher is particularly impressed with how their class has performed all year. They want to be 90% confident that their class has performed on average better than the national guideline of 70%. She takes an sample of 7 papers, and these 7 papers have a grade of 71%, 72%, 79%, and so on. So now they formulate the question. The null hypothesis is that the mean grade of her class is 70%. And the alternative hypothesis, because she thinks they're doing better, and the way she's asked her question is better, she doesn't care about worse. The alternative hypothesis is that mu is greater than 70%. And so this is a one-tailed test. She wants to be 90% confident, so she chooses an alpha level of 0.1 this time. Going back to that online calculator now, so we can say that the population mean this time is going to be that national guideline of 70%. Okay, that's what we're comparing to. And what is the sample? So this time we can just paste in those 7 grades. Choose a significance level, so this doesn't change the answer at all, so, but we'll put 0.1. And we're asking, is it a one-tailed or two-tailed hypothesis? Always, on online calculators, always choose one-tailed. There we can click calculate, and this gives us a p-value here of 0.108583. This time we are saying under the null hypothesis we would expect that t-statistic to have this green curve, and we're going to reject it if it's in that rejection region, which is the upper, because we're looking at greater than, it's the upper 10%. We got a p-value of 0.1085, so we think our t-statistic lies outside of that rejection region. And that means that the probability of observing those 7 grades that we got, given that the null hypothesis is true, is 0.1085. Now that's actually bigger than 0.1, which is bigger than our alpha level, so we don't have enough evidence to reject the null hypothesis. What we saw wasn't extreme enough to go, the null hypothesis might be wrong. Therefore, we don't have enough evidence to reject the null hypothesis. We cannot reject the null hypothesis. That doesn't mean that we accept the null hypothesis. We can't accept the null hypothesis, we don't have enough evidence for that, but we also don't have enough evidence to reject the null hypothesis. Now we'll do an example of a two-tailed test. So a class test consists of 20 questions. Each is multiple choice out of a possible of 3 answers. So an examiner would like to test whether the answers of a given class were chosen completely randomly or not. Okay. A sample of 10 papers had the following scores. So one paper had 7, one paper had 4, one paper had 2, and so on. What's the question in this case? So if they were choosing completely randomly, they would have a 1 in 3 chance of getting the answer right on each question. Therefore, you'd expect them to get 20 over 3 questions right. So now we'd expect the average to be 20 over 3. So we're saying the null hypothesis is that they chose completely randomly. So the null hypothesis, we would expect the population mean score to be 20 over 3, which is about 6.666. The alternative then, this time, is that it is not 20 over 3. If they weren't choosing randomly, either they were choosing and getting things wrong more consistently, or they were choosing and getting things right more consistently. So now the alternative hypothesis is just that it's not equal to 20 over 3. This is a two-tailed test. Let's say we want to be 95% confident. That's a common confidence level to want. So we choose an alpha equals 0.05. So let's use the same calculator we were using before. Our population mean this time is 20 over 3. So that is 6.666. Our sample, we can just paste in those scores of the class, the 10 scores of the class. Choose a significance level of 0.05. Like I said, that doesn't change the answer. It just changes how we interpret the answer. And now, even though we are doing a two-tailed test, we are going to say it's one-tailed. And I'll explain why in a bit. Just calculate that, and we get a p-value of 0.176169. Now we'd like to be 95% confident that our population mean is not bigger than or less than 6.666. So our rejection region, which because of our confidence level of 95% was 0.05, our rejection region now is split between one extreme and the other, being extremely bigger than or extremely less than. So now we're asking, does our t-statistic fall within one of these regions? Which would be, is our p-value less than 0.025? We got a p-value of 0.1762. How do we interpret that? So the probability of observing a sample of those exact 10 scores that we saw, given that the null hypothesis is true, the null hypothesis being that they chose completely randomly, is 0.1762. That is bigger than 0.025. That is bigger than, how do we get that 0.025? That was our alpha level divided by 2, because we had to split our rejection region in 2, into being extremely bigger than or extremely less than. And because our p-value is greater than alpha over 2, what we saw wasn't unlikely enough to say that the null hypothesis probably wasn't true. We don't have enough evidence, so we cannot reject the null hypothesis. If you're wondering now why I said why we didn't put the two-tailed test thing in the calculator, what would have happened if I'd selected two-tailed here instead of one-tailed? Okay, I haven't changed anything else. Calculate that. We get 0.35233. That's just double what we had before. So what that means is that this calculator is changing that p-value for us, adjusting it for us, so that we can compare to alpha, not alpha over 2. But the more standard way of doing this is just getting the other p-value out and comparing to alpha over 2. And that's how I'd like you to be able to do this. That calculator, which gives us our p-value, is making a lot of assumptions, which is how it can assume that this statistic follows that kind of Bellish curve. What are those assumptions? Well, it's assuming that the variable we are using is a continuous variable. It's assuming that we are dealing with interval or ratio data. Now that should have been obvious because we're dealing with means. Means only make sense for interval and ratio data. It was assuming that the original population was normally distributed. It was assuming that all our observations were independent of one another. And it was assuming that we had a large enough sample size. What does that mean? That means we can use these as checks to go, is a t-test appropriate here? So if we haven't got a continuous variable, we can't use a t-test. If we're not having interval or ratio data, then you can't calculate a mean. So that doesn't make sense, so we're not using a t-test. If our data is not normally distributed, then we can't use a t-test, and that's a big check. Okay, that's a very important one. We need to check, are our observations independent of one another? This usually means that all the values are different observations. So for example, in our class test example, all those class tests came from different pupils. If we had a population where some of the class tests came from the same pupil, then they wouldn't be independent of each other because that pupil is probably going to do similarly on both tests. Then we're assuming we have a large enough sample size. The samples I showed you here weren't large enough. 18 was probably okay, but 7 was definitely not large enough. Asking what is a large enough sample size is a difficult question. Okay? The more data you have, the better. If you can do a t-test with 100 values, do it. It's difficult though, and I understand that in a lot of sciences where you perform an experiment and experiments are really expensive or time consuming, getting a large sample size is difficult. So these are the checks that you need to perform before you can carry out a t-test, and you can only perform a t-test and only make those statistical inferences from the p-value that comes out if all these are adhered to.